In example 2, we're not actually being asked to make a graph, even though we are being asked to compare them. So really we're being asked to use what we've known from previous units to sort of describe how these are going to be similar and different from one another. So notice the only difference between them is that numerator value. So that's the A value. And remember up above in that chart, we saw that when the A value is greater than 1 in absolute value, we're going to have a stretch. And when the absolute value of A is between 0 and 1, we're going to have a compression. We also saw that when the A value is negative, we're going to reflect across the x-axis. So the different branches would flip into different quadrants. So let's look at what's going on here. One of the first things you should notice is that A is less than 0. So one thing we would say is that they are reflections across the x-axis. So while the second graph would be in quadrants 1 and 3, the first graph would be in quadrants 2 and 4. So that's what we're talking about there. The other thing we notice is that in the first graph, we have an A value of 1. In the second graph, we have an absolute value A that's going to be greater than 1. So that's going to be a stretch. So since the absolute value of A is greater than 1, this is going to have a vertical stretch. Now, a vertical stretch can be kind of hard to visualize in this case. And if I was in class, I would sort of take a flexible ruler and show this to you, but let's see what we can do. Okay, since I can't do this live for you in class, I can illustrate it in Desmos. Notice over here on the left, I took y equals a over x. So that's basically our reciprocal function, but I made a with a slider. And I said I didn't want a to go any smaller than 1 because we're talking about what happens with the stretch. But what I would like to see is what happens as the A value gets bigger. What does a stretch actually mean? So when I push play, you're going to see what it means to do a stretch. So when I picture this, I almost imagine somebody grabbing the ends of one of the branches and pulling their hands away from each other. And what that does is that takes this point that was like closest to the origin and it pulls it away from the origin. So to me, that's how I visualize a stretch. Now I just snuck in there and I changed the values. And I've now set it so that A is going to be between 0 and 1. And I'm going to take A and start it at 0 for you. Now notice, if we let A be 0, we no longer have a reciprocal function. But let's let it slide away from there. So notice that's still stretching away, right? A compression would pull it back in. So we actually want to go in the opposite direction. So you'll see it get bigger as we go away from 0 and get smaller as we go back towards 0. But we need to think about what's actually getting bigger or smaller. So when we stretch and compress, it's not so much a true vertical or horizontal compression. It's really about this point in here that's closest to the origin decreasing the distance down to the origin or increasing the distance down to the origin. So it's a little bit of a different idea for how we think about stretch and compress. So if I come back to the note sheet, when I say stretch here, what I probably want to say is that the graph that's negative 1.5 over x, that's further from the origin than the y equals 1 over x would have been. All right, let's look at number 3. Number 3 is asking us to make a graph, but this time we have some transformations happening. Namely, we can see that we are translating 2 spaces to the right and translating up 3 spaces. So when I go to make my parent function, I'm going to strip away the transformations and I'm just going to make my parent function based on 1 over x. So no translation. Well, when I do that, I can just pick numbers that are easy to work with because I'm going to be taking the reciprocals of them. So if I have something like 1, well, the reciprocal of 1 is just 1. When I take the reciprocal of 2, I'm going to get a half. So I actually quickly realize it's almost easier to take reciprocals of fractions. So some of my x inputs are easier as fractions than as whole numbers. Now, I can't center this one at the origin because, or in the center of the grid, because this one does have those translations. So if the graph itself goes 2 spaces to the right and 3 up, then my axes want to go a little bit to the left and a little bit down to compensate for those translations. And now here's something that you haven't seen me have to do before. I'm going to actually draw the asymptotes before I draw the rest of the graph. It makes the work much easier. So the asymptotes are going to occur at x equals 2 and at y equals 3. Basically, those translations are where the original x and y axes would have been before the translations happened. This is going to make it a lot easier to make my graph. I can now imagine that 0.23 as sort of being the origin of the graph, and I can graph based on that. So I have the 0.11, imagining that the intersection of the asymptotes is actually the origin of the graph. I have the 0.21, so that's really just here. I have the 0.12, so that's just there. So I can see that my curve fits right in here. So if the intersection of the asymptotes was at 2, 3, this point is at 3, 4. And you're going to find it gets really hard to label very much on graphs like this. So although I'm going to label the 0.34, rather than labeling more points on the curve, I'm going to label the line x equals 2 and the line y equals 3 because that's actually more useful information than a whole bunch of points on that very tiny curve. But don't forget, that's just one branch. There should be another branch in what would have been the third quadrant. So just like we went over 1 and up 1, we also go back 1 and down 1. And we put in the same types of points we had before, and we see that the other branch looks like this. I do still need to label that point. That point is now 1, 2, but I'm probably not going to label anything else on this graph because it just gets a little too confusing to look at. Just like we mentioned earlier, the domain and range are easy to identify if I know what the asymptotes are. I know that the domain allows x to be anything other than 2, and the range allows y to be anything other than 3. Now let's take a look at our last problem. This one's a word problem. A mystery society is renting a Victorian mansion for a murder mystery party. The owner is charging the group, which has 75 members, $650 for the weekend rental, but does not want more than 30 people in the house. All of the members attending the party will split the cost of the rental equally, except that the member playing the dead body does not have to pay. All right, so this is going to be an inverse variation kind of situation, right? I would normally just be taking the total cost of $650 and I would divide it by the number of people going, except one person doesn't have to pay. So I'm dividing by 1 less than the total number of people going. Oh, cost per member C as a function of the numbers of members attending N. Sorry about that. I didn't read through to the end to see that they gave me specific variables that I should be using. All right, so the group has 75 members. So if I'm thinking about the domain here, right, nobody could go. Oops, my domain is going to be based on N. Or somewhere between, why did I put an N? 0 is less than or equal to N, which is less than or equal to 75 from the perspective of the group. But notice, the person who's renting out this home says, nope, 75 is too many. That's not actually the max on my domain. The max is 30. I can't have more than 30 people going. All right. It says, how many members have to attend for the cost to be less than $25 per person? All right. So if the cost is going to be $25 per person, then here's my formula. 25 equals 650 divided by n minus 1. Now, you have some choices. You can just multiply both sides by n minus 1, or you can put a 1 underneath the 25 to make it look like a proportion and solve that way. But I hope in Excel we can handle, let's just multiply both sides by the denominator. So we have 25n minus 25 equals 650. If we add 25 to both sides, we have 675 is equal to 25n. And if we divide both sides by n, we get 27. So that tells us that the number of people who could go was 27. Now, remember, this says the cost must be less than 25, right? So we really didn't want an equals. We want the cost to be less than 25. So 25 is the most that we're willing to spend. Oh, not even nor equal to, just a less than. So we need more than 27 people to go. But wait, we need to look back at the domain. We're not allowed to send more than 30. So the options are actually very limited. We can send 28, 29, or 30 members to this event, but that's the only option to get it for a price that people are willing to pay, but not break the rules of the person who's renting out the mansion.